Swayam Prabha. Digital India. Educated India.
Hello everyone. In this lecture we'll be looking at a simple example problem of free surface flows, which is a uniform flow down an inclined plane. In general, when you have free surface flows such as this, you can also have undulations on the surface, but we'll be looking at the problem of undulations and waves on the surface in a later lecture. One of the simplest examples that comes to my mind right now is the case of a thin tear film that is rolling down your eyes when you keep your eyes open. That's an example of a thin film, and essentially the gravitational force basically causes the thin film to drain if you keep your eyes open for sufficiently long. This also occurs in many other situations, and to illustrate this problem we've considered a simple inclined plane which is making an angle theta. Gravity is acting vertically downwards. It's a uniform flow, hence the thickness of this thin film is constant. We'll call the thickness as H0. We'll also say that it's a free surface flow. Therefore, we know the density and the viscosity of the fluid. The viscosity of the surrounding fluid is 0. The pressure inside is some P. We will determine this. And the pressure outside, we'll call it as just P infinity. And we will also have to define the coordinate system precisely. So I will take a coordinate x along the plane going downwards, and I have another coordinate y perpendicular to the surface. Therefore, the substrate or the surface is at y equal to 0 and the interface is at y equals h0. Now the goal of this analysis is to primarily derive the velocity profile. Obtaining the velocity profile is our goal. We'll make a few assumptions here. Surface tension is constant. Flow is steady. It's also fully developed. And 3, region above the film is passive. With these assumptions, a number of terms can be removed in our equations. If surface tension is constant, then Marangoni effect is gone. If the flow is steady and fully developed, time derivative terms disappear. If the flow is fully developed, then the velocity profile is not changing as I move in x, and the film above is passive. Therefore, the viscous effects from the above gas does not matter to us. Now, one has to keep in mind that if this is just a simple draining film, you need to provide a constant supply of fluid. Otherwise, the fluid would just keep thinning down. This is also true in a pipe flow. If you do not have a constant inlet fluid that is being pushed into the inlet, the standard pipe flow problem that you may have studied in fluid mechanics courses, where you get a fully developed parabolic profile, if you're not constantly pushing the fluid from the inlet, either by a velocity flow rate that is being given or through a pressure gradient, then the velocity profile will eventually slow down and the fluid will come to a halt. Now, another important assumption that we are making is, this is again connected to the fully developed condition, is that the thickness of the liquid film is constant. It is not changing in space, it's not changing in time. To make the analysis a little quicker, I've already written down the governing equations. So here are all the governing equations, and these are just borrowed from our previous lecture. So we have the continuity equation here, and we have the x momentum and the y momentum equation. But before we proceed with these equations and simplify these equations, let's look at what are the boundary conditions that would be relevant. Now let's write down the easy boundary conditions. So the first one is, we know that here we have, on the surface, we have no slip and no penetration conditions. And on the interface, we have interface jump conditions. We will use these conditions to obtain the velocity profile. Let's start by looking at the equations. Now this is a fully developed flow, which means that the velocity is not changing in x. So therefore, I can straight away say that this is 0. You can also say that's because u is only a function of y. It's not a function of time, it's not a function of x. And this immediately gives me the result that del v by del y is 0, and hence v is constant. V is not varying in x, it is also not varying in y. But we also know at y equal to 0, we have the no penetration condition. V equal to 0 implies v equal to 0 everywhere. Remember, v is basically along the coordinate axis is along the inclined plane and perpendicular to the inclined plane. So v is the velocity component perpendicular to the inclined plane, and we have only drainage along the inclined plane, and we have no velocity perpendicular to the inclined plane. This allows us to immediately simplify a bunch of terms in our equations. For example, if v is 0, I can straight away get rid of this term. I have steady state, so therefore this term is 0. It's fully developed, so therefore this term is 0. We do not have any variation of velocity in the x direction, so this term is also 0. Further, this is a gravitationally driven flow, not a pressure gradient driven flow, and therefore I can also say that this term is 0. So this is not a pressure driven flow in the conventional sense. Okay, and therefore the equation just simplifies to mu del square u by del y square plus rho times gx is 0. We'll return to this equation in a bit. And finally, if you look at the vertical component of the momentum equation, all these terms are 0. These terms are as well 0. And what we finally have is these are the equations that we have. Okay. So let's write down all these equations again. We have kinematic viscosity nu times del square u by del y square plus gx is 0, and then I have 1 by rho del p by del y plus gy is 0. These are the two equations that I have. I have two unknowns, velocity u and pressure p. So I have two equations. Let's look at the boundary conditions. We already know that by no slip condition, we have at y equal to 0, u is equal to 0. That's the first condition. This is the no slip condition. Right? And where do we use the no slip condition? If you look at the first equation that I have written down here, let's give these equations labels. Let's call this equation A and equation B. If you look at equation A, then it's a second order differential equation. In fact, actually, I can replace the partial derivative for u with total derivative. And this is a second order differential equation for u, and I can integrate it twice, and I will get two constants, which means that I will need two boundary conditions for u. Let's do that. I'm creating some space here, Ghanshyam. Just remove this. So let's integrate equation A. Twice. If I integrate it first time, I would be getting C1, then I would integrate again, I have these two conditions. I have to determine these two constants. Let's look at the first condition. Zero, and therefore I have the left hand side is 0, the right hand side is 0 plus C2, therefore C2 is 0. Now I can do the same thing for integrating equation B. What do I have when I integrate equation B? I can rewrite this equation B as del P by del Y is rho times gy, and if I integrate this, I get P, which is a function of y, will be rho times gy times y plus a constant, which we'll call it as C3. And we also know the next condition that we have to now look at interface conditions to get C1 and C3. So let's highlight them. So we still don't know C1, as we still don't know C3. So now we need interface conditions. To do this, I've already written down the normal stress balance from the previous lecture. This is done for a free surface flow, and this looks like a fairly complicated equation, but let's make many simplifications based on the assumptions that we've taken. The first assumption we've taken is that the interface is flat. For a flat interface, I know that Hx, which is nothing but dH by dx, is identically 0. And immediately this means several terms drop out in the equation. For example, this entire term drops out. ux fully developed, therefore this term drops out, curvature term drops out, right? So basically all the terms except pressure drop out, and this immediately means P infinity minus P is equal to 0 at y equals h naught. Remember, the interface conditions are at the interface, which is at a distance of y equals h naught, and therefore it means at the interface P at y equals h naught is P infinity. That's consistent with what we have already seen, that you will have a pressure jump only when you have curvature. This is a problem where surface tension is present, but you do not have a pressure jump because there is no curvature, right? So that's the condition that we have got, and now we can use this condition to determine the constant C3. Okay, we label this condition as C. So since P is equal to P infinity at y equals h naught, we have P infinity will be rho g y, that's the y component of gravity, times h naught plus C3, and this gives me C3 will be P infinity minus rho gy times h naught. So now I have basically got the constant C3, and now I can basically get the pressure profile everywhere by saying that the pressure as a function of y will be P infinity plus rho gy times y minus h naught. We'll interpret this more carefully a little later, but now let's look at the tangent stress balance. Now the tangent stress balance, I've not really written anything here. The reason for this is because the tangent stress balance is significantly simpler because we do not have any viscosity at the top, and we also don't have any Marangoni stresses. Significantly simplifying these equations, we can cancel out this term because there is no vertical velocity. Hx is 0, and these terms are again 0, both because of fully developed condition as well as Hx being constant. And this simply simplifies to uy is equal to 0. Or in other words, del u by del y at y equals h naught is 0. That's the condition that I get from the tangent stress balance. So now I've got the boundary condition for velocity at y equals h naught. I can basically look at the constant C1 now and say that determining the constant C1, it says at y equals h naught, we have del u by del y at y equals h naught is 0, and this immediately means viscosity times 0, that's the constant on the right hand side, plus gx times h naught is simply C1. Therefore C1 is simply gx times h naught. Therefore the velocity profile that I now have, what is the velocity profile that I have here? If you substitute everything, you get minus gx by nu y square by 2 plus c1, that is gx into h naught times y. That's my velocity profile. Or this is also nothing but gx by nu times h naught into y minus y square by 2. Now let's look at what is the expression for gx. If I take a small part of the wedge, I have gravity downwards, g. What I now have is, I have the two components of the gravity. This is gy, this is gx, and gx is g sine theta and gy is minus g cos theta. Therefore, I have the velocity profile u of y is nothing but g sine theta by nu h naught into y minus y square by 2. So if I have to draw this velocity profile in this problem, then I have the no slip condition at the bottom and the stress free condition. So here I have del u by del y is 0. Here I have u equal to 0, and this is a half parabolic profile flowing down the incline. Okay. What about pressure profile? The pressure profile will be P infinity plus rho g cos theta times h naught minus y. So when you are at the interface where y equals h naught, the pressure is P naught, but as you go down the interface, as you go towards the substrate, the pressure increases because of gravity. That's just hydrostatic pressure. There are a lot of interesting extensions that we can look for this problem, but we will stop here. And in a follow-up lecture, we'll look at a case where the interface is not flat, but is changing its shape.